Hello, everyone. Welcome to our discussion today on electrical pre-commissioning. My name is Paul Turner, and I help people and projects succeed at commissioning. So I've got a little bit of a presentation lined up for you today. We'll discuss some of the electrical pre-commissioning activities that take place on a typical project. Then I'll go into the live Q&A where we can answer your questions, anything that comes up during the discussion. So let's get right into it. So for today's discussion, I'll go through a little bit of my commissioning experience for those that are new to the webinar format that we've been hosting here regularly. I'll go through electrical pre-commissioning activities on a typical project. I'll let you know about my free training course that I offer, as well as we'll answer any questions that you have on the presentation or any discussions that you or questions that you have in general on commissioning, pre-commissioning, startup, or anything related to those topics. So we're broadcasting on Facebook, YouTube, and LinkedIn. You can tune in and watch on any of those channels, and we'll be gathering any questions on all three of those platforms. So as I'm going through the presentation, if there's any questions that you have, enter them in the chat box, and we'll be gathering them up. And then at the end here, we'll go through the live Q&A, and I'll go through all of your questions that you have. So as you think of a question, just enter it in the chat box, and we'll answer it at the end here. We do regularly host live webinars, so if there's any topics that you think might be good to cover in a future discussion, put that in the chat box as well, and hopefully we'll get that covered in a future webinar. And also there is a webinar participation certificate, so if you stay to the end, I'll tell you how you can access that as well. So a little bit about me. My name is Paul Turner. I'm a professional electrical engineer and a registered project management professional. I have 20 plus years of experience working with complex systems. I live in Canada and I have a wonderful family that we love to spend lots of time outdoors visiting all the beautiful places that are in Canada. Some of the projects that I've worked on are in the aerospace industry. I've built satellites and rockets for the Canadian Space Agency, as well as payloads on the International Space Station. Power generation, I've worked on a 200 megawatt hydro generating station in northern Canada. Power transmission projects, I was the commissioning manager for a 2300 megawatt HVDC link that was a $5.2 billion project that we delivered on time and on budget. Currently, I'm the commissioning manager for a wastewater treatment plant where we're upgrading and expanding the facilities. So if we start with the pre-commissioning activities on site, really the first trigger that's going to take place is mechanical completion. This is the first thing to occur. And typically for electrical systems, mechanical commissioning takes place. So the handover from the construction team to the commissioning team, followed by the pre-commissioning that's done by the commissioning team itself. I haven't worked on too many projects where the construction team has done the electrical pre-commissionings. That's usually a commissioning team's responsibility. So then the sequence would be the systems are installed, mechanical completion takes place, so it's handed over to the commissioning team, and then the commissioning team starts to perform the electrical pre-commissioning activities. Now we'll go through some of the typical pre-commissioning activities in the next few slides here. So some of the first activities or an example of pre-commissioning could be vendor site acceptance testing, or vendor SAT. This is very similar to factory acceptance test, with the exception that now the testing is done on site. So the vendor may have done a certain set of tests in the factory. They'll typically come to site and do some of those tests or all of those tests again on site. This confirms that there was no damage during shipping or installation. Similar tests could be performed as were done in the factory. So if the performance tests were formed on a pump, say the pump curve was measured in the factory, after shipping and installation, the vendor would want to confirm that their equipment is still intact and meets all technical requirements. The performance or the pump curve may be measured again on site to confirm that it still meets technical requirements. So with those two sets of results from the factory and from on-site testing, you get a pretty good idea and can compare to see if there's any differences or any damage or upset to the piece of equipment from the factory to on-site. During the SAT, the vendor can confirm that they have in fact delivered contract compliant equipment and that it meets all technical requirements and is therefore available to proceed with further commissioning. So the vendor will sign off on their equipment saying, yes, it does meet technical requirements. The vendor, the contractor, the owner, commissioning team, whoever's involved there will sign off and say, okay, yeah, this piece of equipment's good to go. Now it can be used for further testing in the rest of the subsystems and systems. So some other typical checks, some of the easier checks would be grounding and bonding checks before the power is applied. The integrity of the grounding system and bonding system needs to be verified. You want to check this before first power is applied because if there is any issues during energization, this is the system that will direct hazardous energy to ground and protect the equipment and protect any people that are working in the area. Grounding and bonding checks are typically confirmed visually or can be measured with a multimeter measuring the resistance of bonds to ensure low impedance bonding to all metallic surfaces in place. So following that, then first power can be applied to control and protection cubicles, communication cubicles, any of the racks that are controlling any of the equipment on site. Once all the cables have been pulled and terminated, then the cubicles can be energized for the first time. Some basic checks as you're going through this would be obvious power polarity checks. You want to confirm that the cables are installed correctly, that you're not going to provide power backwards to a cubicle and cause damage to the equipment or cause any safety hazards. Once the cubicles are energized for the first time, then some of the initial pre-commissioning checks can take place, and this would include uh, communication checks to other cubicles. So if there's a suite of, say, a dozen cubicles, they're all going to be communicating amongst each other, and you want to have some of the basic checks to just make sure that the cubicles are responding to the communications network. Remote I/O checks to distributed devices within the plant, as well as communication with each of the cubicles back to the central control room. Some other checks that we'll go through in a bit more detail in a second here would be hot loop checks, basic logic checks, and these are some of the things that I'm developing in more detail in some of my automation training courses that are coming up in the near future. So moving on to loop checks, prior to mechanical completion, the construction team would have completed point-to-point checks, or I guess another term would be cold loop checks. So that's the electrical verification point-to-point that all the cables and conductors are terminated to the correct terminal blocks. Following mechanical completion and following energization of the cubicles, we can now move into hot loop checks or operational loop checks. So loop checks confirm the integrity of a control loop of the system. Sorry about that. Loop checks confirm the integrity of a control loop of the system from the HMI to the end device, including all cables and instruments. So a hot or operational loop check will confirm from the cubicle that the cabling is intact and that the field sensing device is properly installed, that the field device is properly calibrated, that the field device can successfully communicate with the HMI system, that ranges and set points are correct, and that information is correctly displayed on the HMI. So during these hot loop checks, alarm points are verified by stimulating the field device and confirming that the correct alarms are generated and logged. So without the actual plant process started up and running, let's use the example of a level sensor in a tank. There's no liquid or water inside that tank. So during some of these hot loop checks, you may have to stimulate the level sensor to simulate varying levels within the tank. That could be as simple as just a piece of cardboard on a stick that you're going up and down and allowing the level sensor to measure the different levels of the tank And as you're doing that, you're going to want to see that the corresponding information is showing up on the HMI correctly, that it's scaled correctly, that you've got the right polarity, and that you can read the information correctly on the HMI. And the reason you want to do that is because once you actually get the process fluids in there and everything's working as a system, you don't want to find out that that level sensor is in fact not working. Best to check that out during pre-commissioning to make sure that all the end devices are working before you actually start running the plant as a system. So another pre-commissioning check would be AC phase checks. Before three-phase systems are energized, phase checks are completed to verify installation of each electrical phase in the proper order. If three-phase power is installed backwards, called phase rotation, the system may rotate in the wrong direction, but worse, some equipment can't tolerate incorrect sequencing of phases, and you could potentially damage or destroy some of the equipment if it's not wired correctly. So you definitely want to confirm that the phasing is correct. You can do this by on larger power systems. You may be just visually verifying, say like a high voltage transmission AC switch yard. You can visually see all the conductors, and you're going to confirm that everything is connected correctly from transmission lines to the buswork in an AC station. For smaller power systems, they can be measured. You can measure each phase and confirm that they're correct. You can also use a phase rotation meter that can be connected to the equipment before the power is terminated to the equipment, and that will tell you if your phases are connected correctly. Well, looks like my slides are stuck, so just ignore them for a minute there. So then the next checks we're going to go through are transformer checks. These are tests to be done on transformers before and after first energization. So prior to the first energization, you'll take some oil samples, and these are compared to oil samples that you will take after energization. When you compare the two samples, you can see that if there's any differences between the samples, could indicate there's problems internal to the transformer. If you see additional particulates or elements that are part of the second sample, that could be an indication of off-gassing within the transformer, or any hot spots, improper bonding, anything that could be generating arcing or hot spots within the transformer. You should notice that in your the difference between the two oil samples. As well, winding resistance measurements are taken, as well as insulation resistance. These are typically done in the factory, but sometimes for larger units, they may be done at site as well. You can compare those results from the factory to the on-site results to confirm that nothing was damaged during shipping. Transformer ratios are measured once tap changers are set to confirm ratio of primary to secondary windings. And once the transformer is energized, there's a few additional checks you can do. You can do an open circuit test, and these are performed to measure the no load current losses. You can also do a short circuit test, and these are performed with reduced voltage to the primary winding to measure full load current losses. So moving on to protection relay testing. Protection relays are used within electrical systems to monitor voltage and current and provide rapid response to safe the system should there be any fault detected. So what the relays do is they monitor the electrical properties of the systems, primarily through PTs or CTs, to measure voltage and current of the system, and they sense any disturbances that are in the system and react accordingly to according to the settings that are applied to the relay. So the first thing that you want to do is verify that the correct settings have been applied to the relay. What your engineering team has likely done is conducted a protection coordination study, and that's coordinating the settings of relays, breakers, trip settings, fault settings, all of the protection settings across the entire system. They've done a protection coordination study to determine what those settings should be. So you're going to want to get the settings particular to the device that you're looking at and make sure that those settings are properly applied within the relay. So the relay will communicate back to the PLC systems and the HMI systems, and you want to verify that the values that are being read by those systems are correct. So this includes verification that the polarity is correct for each PT and CT. This is something to watch for because I've seen situations you have a backwards wired CT. As soon as you go to do your first energization, well, the unit's going to trip off instantaneously because it's going to see current that's going in the wrong direction. So you definitely want to make sure that the polarity of your PTs and CTs are correct. But you also want to watch that you're not getting two negatives, a backward CT plus a programming error in the PLC, which is displaying correctly on the HMI, but in fact, you're getting a false reading. I've seen instances like that occur as well. So then you may move on to primary and secondary injections of the CTs and PTs to test some of the relays. Secondary injections can be applied to prove the operation of the relay at one or more settings values. As well, you can do primary injections to prove the stability for external faults and to determine effective current settings for internal faults. You can also use primary and secondary injections to test some of the protection scheme logic to ensure that alarm set points are responding correctly, that the system is logging alarms, and test that the logic is reacting correctly based on the faults that are being detected. So this is a bit of a higher level overview of protection relay testing, but it can be quite involved and there's quite a bit required to do protection relay testing. I see in some cases that owners or the commissioning team may require that the supplier or vendor of the equipment do relay protection settings, but I also know in some of the past projects I've been on, the owner has the capabilities to do their own protection relay testing, and it's definitely a skill to be learned to know all the details of relay protection testing. But I can point you to a really good resource. The individual's name is Chris, and he's at relaytraining.com. If you want more details on relay protection testing, go check out Chris. Go to relaytraining.com and tell him that Paul sent you there. So my slides are cooperating again. That's good. So another important system check to do before any energization is interlock verification. Electrical systems are often designed with interlocks to prevent the system from entering an unsafe operating scenario that could damage equipment or cause harm to people working in the area. So for example, you could have an electrical system that has two incoming feeds from the utility, two redundant power feeds, each feeding one half of a switchgear lineup and the other utility feed powering the other half of a switchgear lineup, normally powered independently. But there could also be a tiebreaker between the two switchgear systems, and you would never want to be in an operating scenario where you have both incoming utility feeds closed as well as the tiebreaker. You'll have phase mismatch and destroy the equipment, big fire, and not a good situation. Lots of safety issues there that could hurt personnel working in the area. So the system would be designed that you could never enter that operating scenario. If both of those utility incoming feeds are closed, there would be interlocks in place that would prevent that tiebreaker from closing. So that if you tried to close it, it physically would not allow it to close. Alternatively, if one of the utility feeds has gone out and the secondary is energized and you do have that tiebreaker closed, the other utility breaker won't be permitted to close until that tiebreaker is opened up. So interlocks are a critical safety factor that must be verified before applying first power to any of the equipment. They're often hardwired rather than relying on automation systems to protect people and equipment. And since there's such a critical safety function, they must be checked prior to energization. All interlocks are verified by operating equipment without the bus voltage applied. The equipment is operated in all configurations to confirm interlocks operate as designed. Essentially, what this would be is a truth table to verify that if this one's closed and that one's closed, then this one must be open. And you want to go through all the different configurations in that truth table to confirm that all interlocks are functioning correctly before applying any power to the system. If you do encounter any issues during your interlock testing, then you're going to want to get that rectified before moving on to the next stages of the tests. So moving on to motor tests. Motors are a common piece of equipment in industrial applications, and they need to be fully tested prior to being placed in service. Initial checks include visual verification of the motor to ensure there has been no damage during shipping or installation. It's fairly easy. You can do a manual rotation of the shaft to confirm it is free and smooth. There's no issues with just rotating the shaft by hand. Examine the motor nameplate and compare the operating and rating values of the equipment so you understand what you're working with. With a multimeter, you'll be able to verify that the motor is properly bonded and connected to the grounding system. Like we talked about earlier, perform AC phase checks to confirm power cables are correctly terminated to the motor. You'll want to measure the motor winding continuity and resistance using a multimeter and compare to the nameplate values. You'll want to measure the phase-to-phase insulation resistance and phase-to-ground insulation resistance. And this is called high pot testing that we'll go through in just a minute here. Once all the checks are complete, the motor can be energized, and initially it would be uncoupled from the piece of equipment that it's running. This is called an uncoupled run, and this allows you to measure the no load current and compare to the nameplate values. Then once that's complete, the motor can be coupled to the equipment that it's running. Say it's running a pump, it can be coupled to the pump, and then under load, you can do the same thing as measure the current at 3 different points and allow the pump curve to confirm rated operation and confirm that the motor and the pump coupled together are operating correctly. So AC and DC high pot tests, what that stands for, high pot stands for high potential or high voltage. And this measures the ability of a dielectric to withstand rated and transient voltages. So high pot tests are the opposite of continuity tests and confirm that no current will flow from one point to another. Voltage is applied between ground and the conductor, and if the insulation between ground and the conductor is sufficient, the application of a large voltage will result in a very small current. Now, the applied voltage and the duration of the applied voltage, those do depend on the local standards and codes in your area, but typically what is done is double the rated voltage plus 1,000 volts for 1 minute. Now that 1,000 volts is to account for any transients in the system. The voltage applied can be either AC or DC, and that'll be determined by your technical specification or local codes and standards. But when you look that up, then you'll be able to apply the necessary voltage for the required duration to confirm that the dielectrics of your equipment are correct. Now, one thing to note is this test does work with very high voltages, so it can be a very hazardous test and typically is done by experienced personnel. So if you're being involved in this test, it's very good to get paired up with an experienced commissioning engineer that's done these types of tests in the past so that you can learn as well how to do them safely and properly. Battery discharge tests. Battery bank testing is important because You want your battery bank to function properly when it's needed in a power loss situation. So you definitely want to test battery bank systems in advance to know that they're available when needed during power loss. So the battery discharge test will confirm that individual cells and batteries meet the technical requirements of the specification. Your technical specification will require so many hours of rated voltage, and cells can sometimes be damaged if they're not stored correctly, if they're not charged and cycled correctly. Then you don't want to be placing a battery system that's already lost half of its life in service. You want to confirm that the owner is receiving full life of the battery system so that it can last for the years required to support the project. There's two important tests to complete for battery tests, which are cycle testing and load testing. So cycle testing subjects the battery bank to multiple charge and discharge cycles to confirm that cells meet the manufacturer's life cycle rating. Temperature and charge discharge rates are measured for a few cycles, and this can be used to estimate uh, the estimated life cycle of the batteries can be estimated from these values. You can forecast based on a certain shorter period of time of cycles how long the batteries will last if they'll meet their lifetime requirements. Load testing verifies that the battery bank can deliver the specified power when required. So a static or a dynamic load is applied to the battery bank and it is discharged to the specified depth of discharge. This length of time can confirm that the battery bank can provide the required power for the required duration of time. So there's another group of systems I'll refer to as balance of plant systems. There's several other electrical systems that exist within an industrial plant, and I'll refer to these as balance of plant systems, and these are really the auxiliary electrical systems enabling the building and support systems to function. So an example would be an HVAC system or emergency lighting and control systems, public announcement systems, and others. Each of these systems require pre-commissioning activities or may be part of a larger system requiring pre-commissioning activities. Other pre-commissioning checks will be identified in the checklist you created as part of your planning phase of commissioning, and you'll want to go through each of the pre-commissioning checks that are defined in your documentation. A lot of those will be out of O&M manuals or your technical specification to go through and check all the required pre-com checks. So one important thing that I want to note here is the deficiency classification during pre-commissioning. Anything that's identified during pre-commissioning is added to the deficiency tracking list that was created during your factory acceptance testing and either classified as a type A, type B, or type C deficiency. Some of these would be for the construction team to address, but some of them may be technical non-compliances depending on the issue being discovered. So a type A deficiency would be anything that must be corrected immediately before proceeding any further with any commissioning steps. A type B deficiency is something that does need to be corrected before handover to the owner, but doesn't necessarily impact immediately the function or operation of the equipment or impact proceeding with any of the commissioning activities. A type C deficiency would be minor in nature that doesn't need to be corrected now and could even be corrected after handover to the owner. An example of a type C deficiency would be a minor cosmetic finish or paint scratch on the wall or something that's not necessarily impacting function or operation of the system. Does need to be corrected, but could be corrected at a later date. So pre-commissioning is complete once you've completed all your checklists and verified that each piece of equipment meets the technical requirements of the project. During pre-commissioning, this is when the equipment is really tested standalone. It doesn't operate and function as a system quite yet. You're testing out each piece of equipment to confirm that it's ready for later commissioning during the commissioning phase. The components really start to come together as a system during the commissioning phase, which we'll leave now for another discussion. So those are some examples of pre-commissioning activities that would be typical on an electrical project. There would be others as well, but those are some of the typical ones. Okay, there my slides are cooperating. Good. So I just wanted to quickly mention, if you haven't already, sign up for my free 3-day mini course. You can get started at commissioningandstartup.com, and this is really a good 3-day introduction, short introduction to commissioning to get an understanding of the process and some of the functions that are required. So if you haven't already, please sign up for that. And now we can move into our live Q&A. So I hope there's been lots of questions that have been coming in, and I'll start going through them. And as you think of more, enter them in the chat window, and I'll go through your questions here. So first question or comment here is Yusuf is looking for comment or advice. Some companies who produce machines don't care about the right safety procedures as well as the factory owners. So that's very concerning to hear. If safety factors aren't being considered, then I would say that needs to be corrected. And if the the company that's providing that piece of equipment just is not interested in safety at all, then I would say that's not a company that anybody could work with. You can't be putting hazards in the workplace that are going to cause issues for operators and owners in the future. If I'm thinking maybe of a piece of an example, if a piece of equipment's being supplied and the company will just refuse to put a guard around a rotating chain or belt or something, then you can't have that type of equipment in the workplace. That's not safe, and you can't be providing or presenting those hazards to the owner. I guess that's a question for the owner or the project, if they're willing to work with that company and then retrofit and install something on site after the fact to make sure that it's safe. If additional guards need to be applied, then that could be an option, but um, not a good situation. If hopefully in your procurement specification, those types of safety guards are being specified, and that would really be a reason to exclude that vendor. If they refuse to or cannot meet the safety requirements of the technical specification, then you'd have to go to vendor number 2 or vendor number 3 that can meet the technical requirement. Next question. Could you tell us what kind of measuring equipment we would use for the test, the good ones? So if you're looking for like a brand name of a piece of equipment, I don't necessarily know the brand names, but some of this test equipment can get quite expensive for some of the primary and secondary injections. I know some of these pieces of equipment can be like on the orders of hundreds of thousands of dollars and many month lead time, 6 months or more lead time. Some of this equipment is very, very specialized. I won't go through the details of model numbers or specifics, but this is definitely something you need to consider when you're getting ready for pre-commissioning. Before you arrive at site, you're going to have a list of test equipment that's required, and usually some larger expenses and some long lead times. You need to plan for those in advance. Often there seems to be a hesitation to want to purchase some of this equipment, given that it's only required for, say, a few months of commissioning activities and may not be needed any further. And given the high price tag of some of this equipment, it can be difficult to get justification for these larger pieces of test equipment. But one thing that I have found to be helpful is if it's a piece of test equipment that may be required for ongoing operation and maintenance of the facilities, often the operations team and the owner will have to purchase that equipment for operations to use regularly during ongoing maintenance of the equipment. And if that can be advanced purchased, say by a few months or 6 months or whatever is required for commissioning, the commissioning team can use some of that equipment and then leave it at site at the end of the project for the operating team to continue to use throughout the life of the system. I have found that that's a good way to use funds efficiently and justify purchases for equipment if it's something that's going to be needed later, is to talk to some of the groups that are involved and see if they've got funds allocated for some of that specialized equipment going forward. So I'll maybe give a bit more of a description on how pre-commissioning is distinguished from commissioning, where some of the activities can blend together very fast. There may not necessarily be a solid line between pre-commissioning and commissioning, given that maybe in the morning you're pre-commissioning the equipment, and by the afternoon it's moving into more system level testing. Sometimes that split doesn't necessarily exist, but I guess the main distinction between pre-commissioning and commissioning is that the pre-commissioning would be testing of the piece of equipment at an equipment level, kind of standalone, just the pump or the motor being tested by itself. Commissioning would be more so testing as the system to make sure that everything is working together, that the pump can communicate with the PLC system and can control the valves and the dosing system, and the entire suite of, say, a dozen instruments are working together. That would be more so the commissioning. That would be, in my mind, the distinction between pre-commissioning and commissioning. So another question we've got here is, what do we need to inspect or check before we start energization of transformers for the first time? So that's a good question. There's varying sizes of transformers. I've worked with small dry type transformers versus huge three-phase oil-filled transformers, and the tests are somewhat similar, but can vary. When you've got an oil-filled transformer, there's a bit more to check. When before oil's filled in there, you can do an internal inspection to see inside the transformer. Sometimes you don't necessarily want to do that. You don't want to go in there and be bumping or damaging any of the windings or insulation in there. You may just choose to have a camera, GoPro on a stick or something. We've done that in the past to visually verify that there was no shipping damage or none of the supports are dislodged in there during shipping. Then when you're filling with oil, you'll take an oil sample of the new oil that's put in. You'll compare that to post energization and see if there is any off gassing in the second sample. That could be due to a hot spot in the transformer or any arcing or um, anything that's not quite correct in the transformer. You can compare between there. Like I mentioned earlier, you can do a winding resistance check, ratio verification once your tap changers are set. There's typically, for large oil filled transformers, will be a control cabinet on the transformer or just next to it. There'd be a whole suite of checks that would be verified there in the control systems to monitor and verify temperatures and thermal properties of the transformers, and communication of that control cabinet back to PLCs and control room communication to verify health of the transformer. How much earth ground should be in a transformer? So that may depend on the design of your system. Um, but I'll give an example because this is an interesting situation that we encountered on our last project, on an HVDC line where there's multiple modes of operating the transformer. You can operate it bipolar, but you can also operate it monopolar with a ground grid at either end of the station. So when we were uh, using the ground grid and injecting into the large ground connection, you do have to consider the resistance of each transformer neutral in the area. So the surrounding area, when we were injecting current into the ground station, was causing currents to flow in the neutral connections of each of the transformers in the local area. So we were getting issues with equipment that was failing, and customers that were raising concerns, and it it can be quite a challenge. And there was a few things that were being looked at to see how how that connection from ground to the transformer was in place and what kind of resistance was there. And really, it turned out that there wasn't enough resistance, and there had to be some sort of other device installed to decouple that, at least to get some of the AC transients out of the neutral connection of the transformers to eliminate some of these power quality issues. Um, so it would depend on the size of your system and the design of the system on how that neutral connection of transformers should be in place. But if not thought about and done correctly, it can certainly cause problems when you're injecting 2300 amps into a ground grid, a ground station there. Then that can cause issues in surrounding equipment that you wouldn't necessarily think that something miles away could be impacted, but through the length of a 1400-kilometer HVDC line, it certainly can and cause issues throughout the length of the province when you've got that type of current flow flowing through the ground there. So is a worthwhile question to bring up, Danila, but will depend on your design somewhat to answer it there. So Bob is asking, what is the difference between cold loop checks and hot loop checks? So essentially, that's the difference of being energized or not. So I would consider a cold loop check basically a point-to-point check without power applied in the loop. There's no communication checks you can really do. It's a unenergized cable, so that would be a point-to-point check to confirm that the conductor is wired from the correct terminal block at one end to the correct terminal block at the other end. That would be a cold loop check. Then once you actually energize, you can do some more thorough loop checks. The hot loop check would actually confirm that the PLC itself can communicate with the end device if that was whatever protocol is being used, if it's Modbus or Profibus or whatever. You can actually communicate with the device. You can get readings from the device. You can confirm that the readings, you can confirm the local reading on the remote device to confirm that that's actually what's being read on the HMI. Comparing those results, you can see that the device has been calibrated, that the proper settings and ranges are applied on the HMI screen itself. Um, and then you can also do another point to distinguish there in hot loop checks is you can do an open loop check and a closed loop check. So an open loop check would be the one-way communication where you're controlling the remote IO device from the HMI. Say you're turning a pump on, and that would be open loop check to confirm that you can in fact turn the pump on. A closed loop check would then be looking for that return communication, so verifying the status signal from the pump to say, yes, it is in fact on. Looking for that closed loop feedback to see that, okay, pump command on, status returned, pump is in fact on. That would be the closed loop check of a hot loop check. Just some different distinguishments of different terminology and how they can be applied for loop checks. So Alaid is asking, can you please give a quick recap of medium-size synchronous generator commissioning? That's a good question. Synchronous generator commissioning, um, that's a fairly detailed topic. Let's assume you're referring to a hydraulic turbine and generator. I have some experience commissioning a hydroelectric plant. So medium size synchronous generator. Initially, when the gates are open and you have a low flow of water, you'll get an initial rotation of the turbine to start generating some electrical power there, and you can verify this in an open state. You wouldn't necessarily be transmitting to the electrical grid at this point. You're just looking for basic electrical power generation in a low power state, but then soon enough, you'll be connected to the transmission grid and you'll want a certain level of power or water flowing through the turbine to generate uh, power through the system there. When you're doing this, initially you're going to be checking for some of the mechanical clearances of the rotating shaft in the between the stator and the rotor. In large electrical systems, this would certainly be done before water is put into the system to verify the proper clearances. Then, well, I guess as part of pre-commissioning, you would be doing all your high pot testing on the stator and the rotor in advance of any electrical power as well to confirm that all the dielectrics are correct of the system. Then when you can start generating power, this is a coordinated effort between the local plants and the central system control operator. Once you start developing power to the grid, that needs to be a planned and coordinated activity. And then eventually you're going to go from low load of say 20% water going through the turbine and go all the way up to full power, generating 80% or 90% or whatever operating flows are through the turbine to generate power out to the distribution plant. This is a whole topic that we could probably talk about in a separate webinar, so maybe I'll just leave it there for now, and we could leave that for a future discussion. For reference with Lotto systems, where is the NFPS standards recommended for safety electrical? National Electrical Code, NFPA standard for electrical, Life Safety Code standard for emergency standby power. So thanks for the question, Haseen. In any of my experience with Lotto, the NFPA has more so come into play during the design phase and not so much lockout tagout. Lockout tagout, I haven't seen referenced to the NFPA standards. Lockout tagout would typically be developed industry standard practices on site related to how the operations team operates the equipment. So in a brownfield situation, you may have your operating team that's already in place that has Lotto procedures already established. If that's not the case, if it's a greenfield site, maybe this is new to the owner that these processes don't exist. In the case of a brownfield site, then you must adapt to what the operations team already has in place with regards to the Lotto authority and request for clearances and permit to work process. If that needs to be newly established, then that's something that definitely needs to be put in place before the commissioning team gets to site. Probably even during the construction phase, there's lots of aspects of lockout tagout that need to take place, and that would have to be in place so that all those systems can be safely executed or safely isolated so that construction can take place and further commissioning can take place. But maybe I just haven't come across it, but I haven't seen that the NFPA standards have come into play with regards to lockout tagout. But anybody on the discussion here, correct me if I'm wrong. If you have experience working with Lotto systems and in relation to NFPA, then please throw out your comments here, and hopefully we can connect the dots there. So another question I've got from Olaid is for the grounding and bonding checks on equipment located on offshore platforms, can please explain their specific peculiarities? That's an interesting question that I've never really thought about too much. I've never worked on an offshore oil platform, so I can't say what the specific peculiarities would be, but that's an interesting thought. Where is the central ground location? I would assume that it's through uh, the legs, the down to the seabed there, but maybe someone can comment further on that if they have any experience working on offshore platforms and any of the nuances specific to station ground on an oil platform, either anchored to the seabed or if it's a floating platform. What are the peculiarities that could exist in that type of situation with regards to a ground? Okay, if there's any more questions, please submit them and I'll continue to answer them. We have a few more minutes here. I'll I'll maybe give a couple more minutes and see if there's any more questions here, and if not, we can conclude the discussion. One thing I would like to maybe encourage is even during pre-commissioning, this is still a good time to get the owners operators involved in the commissioning process. Um, when you're looking at the equipment during pre-commissioning, it's a great time for the owners operators to get hands-on experience of the equipment to see any issues at the equipment level. They'll get lots of opportunities during commissioning and startup to see equipment at a systems level, but often the operations team, that's their primary function would be for, say, operation and maintenance of the equipment. So they're working at the equipment level. And pre-commissioning is a great time to get the operating team right down to the transformer, to the control cabinet of the transformer, and verify and see exactly what's going on during the pre-commissioning, because they're the ones that may have to troubleshoot it in the future. They're the ones that'll have to do the maintenance tasks required on it, and this is a great opportunity for them to get involved as early as the pre-commissioning phase. I always encourage from an operational readiness standpoint to have the operating team involved in the entire process so they can see the process, they can understand the equipment, and they can become more familiar with the systems as it's being handed over. So they have a level of confidence to be able to operate and maintain the equipment going forward. EHV cable high pot test conducted. What is the criteria or standard checklist? So that's going to depend on your local codes and standards. Typically, like I said, for a high pot test, it would be double the rated voltage plus 1,000 volts for 1 minute. I believe that's the IEEE standard that I'd be familiar with in the past. That's what we would use in North America. I'm not sure if it varies elsewhere in the world, but applying that level of voltage for 1 minute and measuring the current that's dissipated through the dielectrics would confirm that it can meet the IEEE standards. That may be different elsewhere in the world, and if anybody on the discussion here has experience with that elsewhere, if it's different elsewhere in the world, please let us know. All right, so I'm not seeing any more questions come in. I appreciate everyone's questions. They're awesome questions that have come in, and I'm happy to answer them. I do see some comments here on the recorded conversation, and that will definitely be posted on LinkedIn, YouTube, and Facebook. I'll send out a link maybe in a few days once we get it posted online. We typically have a write-up discussion on the presentation and the questions that have come in here too, so you can check that out. And I'll send a link to everybody to check that out. Also, everybody would like to receive the certificate with regards to participation in this webinar. I can pull that up here and show you. This is what the certificate will look like. That's just a sample of it with my name on it. But when you go to this link here, commissioningandStartup.com/webinar-cert, you'll be able to enter your name and the certificate will be sent to you within a few minutes. Now, the system we have set up takes a few minutes, so if it's not emailed right away, maybe allow 10 or 15 minutes, but it will come through eventually and you'll be able to receive your certificate. And when you do, then you can download it and if you like, post it online or whatever you'd like to do with it. Tag us if you do. So I hope everybody enjoyed this discussion. Our next discussion on commissioning is planned for September 17th, and I'll send out a link if you'd like to join that next live web.